Okay, so finish at the earliest, fine. So so we will do this part of the story. So one of the most important thing that we need to learn is how to program a parallel machine. Okay. Now what I am trying to teach is some small tidbits of how to go about programming a parallel machine. This is a completely an algorithmic treatment. Okay. Then there are courses on concurrent programming, there are parallel programming courses, programming for high performance computing computers, or high performance computing courses which deal with parallel programming. That is part of your curriculum and electives. So there are many electives in the department. The course on concurrent programming will also teach you much more about this. But what I am trying to tell you is how can I model a parallel computer, how can I model a computing on a parallel computer. I think that is very much necessary, and I think it should be part of a computer organization architecture course. Okay. So like how there is an algebraic model of computation for your sequential computing, single core computing, right, based on which you have got all your big O notations, right, order n square, omega n square, you derive those things based on that algebraic model of computation. Now there is a parallel random access memory model of computation, which you call it as the PRAM model. PRAM here stands for parallel random access memory. Now there are a set of processors, they are all writing into the same memory, correct, and there is a bus that is connecting these processors, that as we had seen in the earlier part here, right, and this is a symmetric multiprocessor system also, meaning all processors have equal capabilities and they can read or write from any location in the memory. Okay, right. So now at any point of time there will be a token, whoever has the token will come and access the memory. I can't say, while I am writing the algorithm, I can't say who has the token. Okay. So let us take one timestamp. At the timestamp there are 4 of us, anybody can have a token, but at the timestamp, okay, every fellow will have something to read or write from memory, right. At that timestamp every fellow will have something to read or write from memory. Whoever gets the token first will write or do, we'll call it as access the memory. Access is a word used for both reading and writing. So everybody will have something to do with the memory, whoever gets the token will access. So when I run the program again, let us assume the same time step or same step, the token may be with somebody else also, right. So at some point of time, so let us take all the 4 programs are running, they are trying to do one job together. I go and take some time slice. At that point every fellow will have something to write into the memory or something to read from the memory. If it is the case that at any time stamp I take, I stop the algorithm, no 2 fellows are reading or writing from the same memory location, then it is called exclusive read, exclusive write, parallel random access memory model, right. I stop the program at any point of time, I just stop it, freeze, there is a game called freeze, freeze. There what happened, now I will say who all want to do what with memory, then I find out no 2 fellows want to read from the same location or no 2 fellows want to write into the same location, then it is called exclusive read, exclusive write, parallel random access memory. So if I write a program, such that at any point of time I freeze that program, I write a parallel program, a multi-threaded program where each thread will execute on each of these processors. I write a program in such a way that at every time step I stop, I say freeze, what will happen, at any time I go and say freeze and I look at all the processors what they want to read or write, no 2 processors want to read or write from the same location. So no two fellow will read the same location also. So that means as processor P1 I want to do some access, it will be some location A1, like that A2, A3, A4, none of these locations will be equal, they are all different. Then this is called a exclusive read, exclusive write, parallel random access memory model, right. Now if that program is such that two fellows want to read from the location, there can exist at more than one fellow who want to read from the same location, but no two fellows will write into the same location. Then it is called a concurrent read exclusive write model, okay, right. So there will be several, this fellow wants to write to A1, this fellow wants to write to A2, this fellow wants to write to A3, read from A3, and this is read from A4. A3 and A4 can be the same because they are trying to read. So more than one fellow can read from the same location, but no two fellows write to the same location. He can write to different locations. Then that type of a model is called concurrent read exclusive write model. The third one is any fellow can read or write from any of the location, then it is called a concurrent read concurrent write model, okay. So there are three types of models, the EREW model, which is exclusive read exclusive write, wherein I freeze at some point, no two processes will read or write into the same location. A CREW model, where I freeze at a point, two fellows can read, one or more fellows can read from the same location, but no two fellows write to the same location. There is a third model where any number of people can read from any location or write into the location, okay. So the program that you write may satisfy one of these criteria. So absolutely there is no issue in EREW, absolutely there will be no issue in CREW also, right, because it is only reading, but there can be one specific issue in CRCW. What is that issue? Let us now start little more in depth. Now we say deterministic algorithm. What is why it is called deterministic algorithm? There are two varieties of algorithm, right? Deterministic algorithm, randomized algorithms, right? Do you know randomized algorithms? You have read randomized algorithms? So what is a deterministic algorithm? For a given precondition, the post condition is well defined for every instruction, for every step in your algorithm. Then it is called a deterministic algorithm. What is a randomized algorithm? For every step the thing is not well defined, obviously. So toss a coin, I don't know whether it will come as heads or tails unless you have rigged a coin, okay, right, followed. Now the parallel algorithms that I am going to write should also be deterministic, in the sense after every time step I should get the same result any number of time I am executing. See, suppose I am executing a program toss a coin, right, first time I execute it will give me head, second time it will give you a tail, so we don't know the output. But what we are interested here is to run deterministic algorithms on these parallel models, right. That means I run it once, I stop at some time t, I see the results times some time step t, not time, step, I should get the same answer irrespective of whichever time I am running. So one time I run, I should not get an answer A, another time I should not get another answer B. That contradicts the definition of determinism or deterministic nature of the program. Now with EREW, do you think there will be a problem with deterministic execution? No, correct, it is obvious, right. With a EREW we will not have a problem with deterministic. With a CREW, will we have a deterministic? No. With CRCW, will there be an issue with deterministic? Yes, right. The reason is both of us want to write at the same point of time. He is writing 2, I am writing 1. So one time when I am executing, if the token is with him, then what will be the final value? 1, because token is with him, he will write 2, after that token will come to me, I will write 1, right. In another time the token is with me, I will write 1, then he will get the token, he will write 2. So at the end of this step, one time it will be 2, another time it will be 1. So when I write an algorithm for the CRCW model, correct, I should see that at any point of time, if two fellows want to write into the same location, then they should write the same value. Right? So when I am designing an algorithm for the CRCW PRAM model, I should ensure that if two fellows want to write into the same location, then they should write the same value. Acha, are you getting what I am saying? Followed? If it does not happening, then what I told would happen. Right? So he wants to write 2, I want to write 1. If he gets the token, the answer will be 1. If I get the token, the answer will be 2. Correct? Now we will design algorithms for EREW. CREW is just a little bit larger extension of that. So we will write one algorithm for EREW, then one more algorithm for CRCW, and that we will do today. We will finish this today. Okay. Now this is known to you, the recursive doubling technique. Now I have 8 processors, right, numbered 0 to 7. Of course this 0 processor will just do nothing. Right. I want to do the prefix sum. So I have 1, 1 minus 2, 3 minus 2 plus 1, 7 plus 3 minus 2 plus 1, minus 8 plus 7 plus 3 minus 2 plus 1, I want to move it. So this we have already seen. Where did we see this recursive doubling technique? Where did we see recursive doubling? Carry lookout adder. So on what operator can we do recursive doubling? Associative. It's also called some hyphen data. So we saw this recursive doubling technique. So what we do? We just add. So every processor is given one location. Every processor is given one location, and what it does? It reads its value. That's one time step. Then it reads its value that it is pointing to. That's a second step. Adds it and stores it back where? In the same location. And if it is pointing to 0, then basically it doesn't read that value. It knows it is a 0. So 0 is put like a sentinel for. Okay. So what happens? At the first step, everybody will be reading its own value. So it is exclusive read. Right? And in the next step, it will be reading its neighbor's value. In this case, it is only reading. Nobody reads from the same location, right? It is this fellow 7 will be reading from 6, 6 will be reading from 5, 5 will be reading from 4, 4 will be, and 1 will not be reading anything. So, right? So it's again exclusive read. After that, what it will do? It will add minus 15 plus 6 and store it here. It will be minus 9 or whatever. Okay? So it is again exclusive write. So at every step, I am doing only. Every processor reads from some location, no two fellows read from the same location, and they write to one location and no two fellows write to the same location. So this is very much fitting our EREW algorithm. So first step, what will happen? This is what happens. Everybody would have read themselves and their neighbor, and then this is how. In the second step, again you see this fellow will be 7 will be reading. 7 will be reading from 5, 6 will be reading from 4, and so on, right? So this processor will read minus 9, then it will read minus 1. So when this processor reads minus 9, this fellow will be reading of minus 1. So the processor will read from itself, then where it is pointing to, and no two fellows point to the same location. Okay. So at the end of this, so second step also can be executed as EREW. Similarly, third step. Okay. Similarly, fourth step, right? And I don't read this 0. Okay, this is just a sentiment. So your this is sum. Sum is a semi-group operator. What, Raghav? Sum is a semi-group operator, and so this entire prefix sum can be carried out with in EREW PRAM model. You are able to understand what I mean, right? That is what I mean by steps. So at the end of every step, you do a barrier. I have already taught you barrier, right? So read this barrier. Then do this barrier, then write barrier. So I can put barriers, and then so that I synchronize such that no two fellows read or write into the same location. And that is where you need a barrier to execute, right? Are you able to get this? So this is one. So what happens? How many processor I have? N processor, log n time I can finish, right? Right? So I had 8, I finished in 3 steps. So n processor, log n time, I can finish this. So like this I can do prefix minimum, prefix maximum, prefix multiplication, everything I can do n processor log n steps. Okay. So now I will introduce another small thing called, I hope I have that. Okay, I will introduce Brent lemma. Sorry, I didn't put the slide here. So I will just see. So what if I have n processor, I can do in order log n time. Okay. What if I have n by p processor? If I have p processors, what if I have p processors? So what I will do is, what is the speed up I can get? This is actually called as, this is processor, this is time. Processor into time should be equal to complexity of the best known sequential algorithm. Right. So I have n processors, log n time. Is n log n, is it the complexity of doing prefix sum? What is the complexity of the best known sequential algorithm for doing prefix sum? What is the complexity of n, right? So n log n is not equal to n, right? N log n is not equal to n. So this is not an optimal algorithm. So what is an optimal parallel algorithm? An optimal parallel algorithm is one in which the processor into time product is equal to the complexity of the best known sequential algorithm. That means what? You have equally split the workload among the different processes. That's what it means, right? If this particular condition is satisfied, that means I have equally split the workload across different processes, right? So in this case, the PT product is n log n, but the best known sequential algorithm will take n unit of time. So n log n is not equal to n. So this is not an optimal algorithm, recursive doubling. So how will I make it optimal? So we use something which is very trivial. Let us see how it is happening. So suppose I have p processors.
Why are we quantifying complexity as process, number of processes into time?
Because that's the total work, no? See, if I have split the work across all the fellows equally, then it's an optimal way of doing. The best known sequential algorithm is n, some complexity. This is the best known. So I can only do as best as this. If I do something better than that, then that will cease to be the best known, correct? Right? So if I say that each processor will do this much amount of work, if I take the sigma of the total work is better than the best known sequential algorithm, then I can make the same processor do one by one after this, and I will get a still better known, better sequential algorithm. Are you getting this? See, the best known sequential algorithm, say let it take 100 units of time, right? Suppose there are 4 processors, I have a parallel algorithm such that each processor can finish in 22 units of time, right? That means what? I'll ditch 4 processors, I'll take one processor, do the same task one after another, then it will finish off in 88 units of time. This contradicts the fact that this is a best known sequential algorithm, correct? Right? So if I have the best known sequential algorithm, then I have this many amount of processors and this time. So this processor into time should be equal to the best, it can be best equal to the best complexity of the best known sequential algorithm, correct? So that's the funda. Now if it is not, then it becomes a suboptimal algorithm. This is a suboptimal, whatever you have seen. So how to make it optimal? We will not have n processors, right? Suppose I have 1 million numbers, will I have 1 million cores? No. So essentially I will have some p processors, p is a constant sometimes. So what we will do, we will split up into n by p buckets. So n1, let me call it as bucket 1, bucket 2 till bucket p, each having n by p numbers. Okay? Okay? Do you understand this? Now I will do the prefix sum so I will give one processor to each one of them. Okay, I'll just go to, sorry, I'll go to that. So so totally there are n numbers. So I will put it into bucket B1, B2 to BP. Okay, so n numbers, P processors. This is ideal situation, right, where n is very much larger than P. Okay. Now I will put equal buckets, so each will have n by P each. Right. So I will do the prefix sum of each. I will do the prefix sum of each. How much time it will take, and I'll assign one processor. I'll assign P1, P2 to P small p. So I'll assign one processor to each, and ask them to do the prefix sum for each one of that, and they will do it concurrently. So how much time it will take? N by P time. At the end of this, what will happen? I will have one A1, A2, A3, A4, AP, right. This is the prefix sum of the first n by P elements here. The last, this is a sum. What will be the last, after I finish the prefix sum, what will be the last element here? It will be the sum of all these elements here. This will be the sum of all these. A2 will be the sum of all these elements. A3 will be A4, A, correct? Do you understand this? So after I finish this prefix sum in each of these individual blocks, the last element will be the sum of all the elements in that block. What is the final answer? If I add A1 to all these elements, right, then that's the final answer. If I add A1 plus A2 to all the elements here, then it's the final answer. If I add A1 plus A2 plus A3 to all the elements here, that's the final answer. If I add A1 plus A2 plus A3 plus till AP minus 1 to all the elements here, then that's the final answer. So what I should do, now I have A1, A2, A3, A4 till AP. I will do the prefix sum of this. Then what I will get? I will get A1, A1 plus A2, A1 plus A2 plus A3, A1 plus A2 plus A3 plus A4, and one A1 AP minus 1. Okay, I will get this. Now I will take this A1 and add it to all these fellows here. I will take this answer and add it to all here. I will take this answer and add it to all here, and so on. I will take this answer and add it. Okay. Now I get the final answer. So how much time will it require? So I took n by p time already for doing this individual computation. Then how much time will I take for? I have p processors and I have p elements. How much time will it take? Log p time to find this sum. Then again I take one number and add it to every fellow. How much time will it take? N by p time, right? Because I take one number, each processor will take that number and add it to the list of this. This will take A1 plus A2 already computed and add it to this. So they will do it concurrently. Again it is n by p time. So this is nothing but 2 n by p plus log p. Since n is very much larger than p, this log p goes off. So this is order n by p. Now number of processors is p, now time is n by p, p into n by p is n, and this is an optimal algorithm. Yes?
For the prefix sum algorithm, are we allowed to query on any index I?
Yeah, like, so this is recursive doubling, no? You have already thought of it.
But like any given any I, it has to give the sum of all numbers from 0 to I, right?
No, but you just have these p locations and just execute the recursive doubling that I taught earlier.
Yeah, no, this will give the total sum, that's fine. But
No, it will not give, sorry, it will give A1, A1 plus A2, A1 plus A2, A plus A2.
yeah, it will give all that. But like
After that, the processor, each processor will read exactly one of these locations. So P2 will read A1 and add it to its element.
yeah.
At that time, P3 will read A1 plus A2 simultaneously and add it to this element.
So like what we're asking is, suppose there are 10 elements and
It's an array.
yeah, it's an array. And if I give the input as 3, it should give the sum from 0, 1, 2, 3.
Why you need?
Like is that a functionality of prefix sum or just adding all the numbers?
Adding all the numbers.
Because in our previous recursive doubling, since we're doing single element, we can given in index.
No, prefix sum is to create an array where it is all sum of all prefixes.
But we have also solved a subproblem that given an index I, we can give the sum from 0 to I, right?
Where did I solve?
No, like
Here
implicit.
also I can solve, no?
No, here it will not work because you are grouping n by p. So if the index is like modulo n by p 0.
Yeah. At the end you will get, no?
No, but like if the index is modulo n by p only, then it will work, right? Else you'll not get
why?
the.
Why?
So because
It's not numbered 1 to n by p. Yeah? I can number it. No, this processor has to read. Processor P2 will read from n by p plus 1 to 2n by p. Yeah.
say if I want to index something like 3 by 2 n by p, then I'll have to go to that index and then add a1 and so on. So
Prefix sum is you will do for everything and query on this. That's what we have been doing. Why should I say one? So I want to stop with I. Yeah.
To query on any
Yeah, I can query. No. You set up. You finish the whole computation, then take from that location and take the prefix sum. Right. Still you can do. So if I am given 100 numbers, I will do the sum for 100 and then query on element. That is also possible here also, right?